So this is the second part of the video of the first section of notes of static equilibrium. Here what we're going to talk about is something called stability and balance. So there are two different types of equilibrium. Now we have something called stable equilibrium and we have something called unstable equilibrium. Now stable equilibrium is referring to a state where when an object is displaced from its equilibrium point, it will always return back to that location. Now, the most common example of this is a pendulum. A pendulum is normally in equilibrium at the very bottom of its swing. If you displace it, it will swing back. It will swing back and forth, but eventually it will relocate to that location. Then we have something called unstable equilibrium. Basically the opposite. You displace an object and it never returns to its equilibrium state. So a perfect example is a pencil. So you have a pencil. You technically can balance a pencil on its tip or even on its flat edge, but the moment that pencil is slightly displaced, it's going to fall over. So this is a scenario of unstable equilibrium. Now, I always think of, when I think of stable equilibrium and unstable equilibrium, I think of a scenario of a valley and a hill. So in a valley, its equilibrium state is right here. Now, if I displace this a ball that's at the bottom of a valley to over here, well, it's going to fall back down to its original location. Same thing if I put it over here. It's going to fall back down to its position. This would be stable equilibrium. Now, on the flip side, a ball placed on top of a hill would be in what's called would be in the unstable equilibrium, because the moment it gets moved past maybe over here or over here, it's going to end up falling down the hill. Now, of course, the world is not completely black or white. It's not only stable or only unstable. A lot of times what you'll have is a combination. So going back to my analogy, it'll be like having a valley next to a hill. It'll be stable within a certain range, but once you go past it, once you put it on top of this hill, or maybe not there because that would still go into its equilibrium state, but if you put it over here, all of a sudden now it's going to fall back down the other way and not return to its initial state. So this is basically how balance works. Once the center of gravity of an object moves past its base of support, basically where it can be in stable equilibrium, it will switch to a state of unstable equilibrium. Now, to visualize this as easy as possible, you can think of a fridge. So a fridge has its base supports at the feet, these two edges here. The center of gravity is pretty much right in the middle. If you push it a little bit, it'll always return back to its original spot like this, like normal, because the center of gravity is still on this side of the base support. The net torque will cause it to rotate this way. However, if you push it far enough and this center of gravity actually goes past this base support, like in diagram C, we end up getting a situation where now the torque's in the other way and it's going to cause it to fall and become unstable. So a really interesting thing that you can do is, in order to make a quick buck, is you can bet a friend that if they put their heels and the back of their legs up against the wall, it would be completely impossible for them to bend over and touch their toes without falling over. Now, I want you to think about, why do you think this works? And is there a way when this won't work? So pause the video and think about this for a second before we go over the answer. So the reason this isn't going to work is because humans actually have our center of gravity around the middle. So here's my perfect little drawing of a person. So this is the top part of the person, this is their legs, and this is their foot, and this is the wall. Perfect, perfect, perfect. Could have been an artist. So when a person bends over, their center of gravity is right about the belly button. I think it's a little bit above the belly button, depends on the person. And our center of balance is going to be right near the tips of our toes, right there. So when we are in this weird setup where our entire back part of the legs, where the heels, the calves, the hamstrings, everything is up against the wall, our center of gravity is placed way over this support. So the support's going to be over here, the center of gravity is going to be over here, and we're going to have a net torque causing us to go this way. If you don't believe me, you can try this yourself right now. Now, because of this, you'll actually notice that when you look at someone bending over, you'll notice that their legs are always kind of arched backwards. Even if this person kind of has a rounded back, but even if they have a flat back and they keep their legs straight as well, you'll notice that the legs are always kind of going off on an angle in order to allow for their body to kind of go down this way. And that's so that their center of gravity, which is for this guy right about here, is kept in front of the balance. So pretty interesting thing to know. Now, going back to part B where it says, when will this not work? Well, if I look back at my perfect drawing here, I want to make sure that my center of gravity is a little bit closer to the wall. In fact, I'd want it closer to my legs. So if you have a scenario where a person is have a very low center of gravity, so all their weight is pretty much in their legs, and they don't really have much on the upper body, then what you'll end up having is a scenario where they actually probably could touch their toes while up against the wall. So this is probably the only time that you'd get away with this, is in this one case of having a very low center of gravity. However, if you have a friend who's works out and has definitely skipped leg day, then you'll easily be able to win that bet. All right. Now, another thing that we need to talk about is elasticity and stress and strain. Now, this is going to become extremely important more for the people who end up leaving this class and moving on to the engineering section. So a lot of you should have learned about Hooke's law, that when we have something that stretches like a spring or a rubber band, when we pull or compress it, it's going to have a force that's related to its spring constant and the amount that it elongates. And we end up getting this proportional relationship between force and elongation. This is the most common relationship that you normally see. Now, anyone who's ever played with a slinky knows that when they stretch it, the slinky comes back to its original spot. But once you extend that spring past a certain location, it technically never goes back to its original spot. What that is there's an extension to this graph that deals with what's called the plastic region. Basically, what ends up happening is the object starts to become deformed past a certain limit. And then if you keep stretching it, it'll eventually start to break. So what we are going to be focusing on is mainly this section here, is the fracturing part. Now, when we start talking about this whole elongation for objects, basically for non-string objects, we're going to use what's called the Young's modulus. You can think of this equation as essentially being like Hooke's law for non-springed objects. So our variation on the equation ends up being this. So we have delta L, which is our change in the length of the object. We have E, which is our Young's modulus, the force acting on the object, the area, the cross-sectional area of the object, and the original length. Now this F and A is essentially the pressure acting on the object, and this value of Young's modulus is dependent on the material that you're using. So an object of copper has a different Young's modulus than an object of silver. This is given to you on in your textbook. So when you're doing problems, look through there. One thing that I'll note is that if you're going to use something on the test, if I'm expecting you to use this equation on the test, I will give you Young's modulus. All right. So from this, we can actually come up with two equations dealing with what's called stress and strain. Stress is essentially the pressure on the object, so it's the amount of force over the area that's applied. And then strain is this ratio of change in length over the original length, essentially how much you're applying and how much you're getting out of it. Like I said, this becomes a lot more important for the engineers in this class. So we can rework this equation to get this equation for that relates Young modulus as being a ratio between the stress that could be applied versus the effect on the object, the strain on the object. So here's a practice problem. You can pause the video and work on this yourself, and we'll go over it in a second. All right, so what we're going to do is we're going to use that equation. We have to look in the textbook to figure out what the steel piano's Young modulus is. And we're going to solve it for tension. So I'm moving everything to one side. Now, these three values we know, the area is not given to us. So what we have to do is use the cross-sectional area of a wire, which is going to be pi r squared. So for those who don't know, a wire is cylindrical. So the cross-section is a circle. Hinted at the fact that they mentioned diameter. So what I'm actually going to do is, because they give me diameter, I'm actually replacing radius with half diameter. If you want to, you could just not do that and just plug in 0.1 for this, 0.1 centimeters, making sure to convert. But once you plug the numbers in and you convert your numbers where you need them to be, you end up getting about 1,000 newtons. So 1,000 newtons is going to be applied to this piano wire in order to stretch it this quarter of a centimeter. All right. Now, there are three different types of stresses that you can have. So you can have stress caused by tension, stress caused by compression, and stress caused by shearing. So tension, what we've been dealing with, is where we stretch it out. It's getting longer. Compression is it's getting pushed together and getting smaller. Typically, for most objects, there's actually no real difference between tension and compression. Shearing, on the other hand, tends to be a little bit more different than the others. This is where you have essentially two opposite forces on the top and bottom, and it's going to cause them to move parallel and anti-parallel to each other. So essentially sliding across each other. And usually the way that someone's always described it is like, think of putting your hand on the top of a textbook and then just moving the top layer over, and you end up turning it into from a rectangle shape to like a trapezoid shape. Or not a trapezoid, yeah, we'll go with that, trapezoid. So the big thing here is, while some of these values are going to be the same for some materials, there are actually some materials that are better under certain scenarios. Like some objects are better under tension versus compression. I forgot exactly which one it is. I think glass. Glass, I know, is much stronger on one of these types versus the other. I want to say it's stronger under compression, that it could withstand a lot more compression than it can tension. Don't quote me on that. But this ends up being a huge thing for the engineers, because when you're designing stuff, you need to be able to understand what type of forces, what type of stresses is an object going to experience. Is it going to be experiencing a lot of tension, or is it going to be experiencing a lot of compressions? And if it does that, what materials should you use to make it so that it is able to be strong under those cases? Now, with the shearing, you actually have to do a slightly different thing. It doesn't use a Young's modulus. It uses what's called the shear modulus. Pretty Nothing else changes but that. Again, it's given to you on the reference table. And it's the value is somewhere between 1/3 to 1/2 of the Young's modulus. So again, most objects tend not to be able to withstand more as much shearing as they can tension and compression. Now this is actually an interesting thing to think of, is imagine a beam, or better yet, since I think everyone's probably done it at least once, one of those cheap rubber combs, and you take it and you bend it. There is actually two different types of stresses going on. There's a compression stress and a tension stress. Now, it's important. It's actually interesting to think about how those two are actually going to be different for this object. Like I said, for most objects, these values are going to be the same. But if you ever recall bending stuff, you'll notice that you start to get deformation on one side versus the other. Now, if you remember, if you want, you can pause this video and think about it yourself, which side ends up feeling more deformation. But if you remember, it's always going to exert on the outer side. So like if you take a comb and you start bending it, it's the outer side that starts to start getting deformed and start turning white. Now, the values should be the same. If we look at this equation, I'm just going to say that this is the Young's modulus, but the Young's modulus is going to be the same for the object. The forces are the same that is being exerted on. The cross-sectional area is the same, or actually no, sorry, the force won't be the same, but the cross-sectional area is going to be the same. They had the same original length, but something's going to cause this force to be different. And it actually turns out it's the change in the length. When you have something bending like this, these two sides are actually experiencing different change lengths. Inside this compression side, it's not changing its length as much as out here. If this was changing its length by, like compressing by, let's say 0.2 centimeters, then out here it would be 0.3 centimeters. So it would explain why the outer edge of objects tend to experience fracture before the inner side, because even though their Young's modulus are the same, this is going to be stretched longer than this is being compressed. Now, this kind of will end up getting used later on when we start talking about fluids and thermodynamics, but we can actually take that equation and relate it more to a three-dimensional state. So instead of using linear length and original linear length, we use three-dimensional volume. Instead of force and area, it's better to just talk straight about pressure, since fluids tend to, that's something that we can actually deal with more with fluids, is the pressure acting on an object. And instead of a Young's modulus, we have what's called a bulk modulus. Again, like a three-dimensional value. Now, like I said, at a certain point, when the stress is high enough, we end up getting a fracture where it will actually break. Now, once again, in the textbook, you'll have a table of all the stresses, all the fracturing stress that an object can withstand before it breaks. So again, whenever you hear this and you start seeing questions dealing with fracturing, it's usually referring to calculating stress and using the value from the textbook. Now, in order to make life easy, a lot of times engineers use what's called a safety factor. If anyone's actually met an engineer, you'll know that they don't take the most precise measurements. And for a lot of people, they think that that's super weird. They don't realize that a lot of times what engineers do is they multiply values by a safety factor in order to take into account unexpected stress. So for example, if they make something so that it can withstand 500 pounds, typically it can actually withstand a little bit more than 500. It's just that they want to make sure that it doesn't get close to that fracturing point. Usually the safety factor is the amount of allowable stress over the calculated stress, or the modulus over the stress. I have some bonus questions at the very end of this, at the end of the PowerPoint, where you'll see how a safety factor can be used in. Again, this is something for the engineering students. So going back to the fracturing thing, we have this. Going back, it's the same piano wire, and we want to know how much tension is required to break it. So pause the video, work on it in a second, and we'll go over it. All right, so we use the stress from the textbook. It says, well, actually, I gave it to you here, but the textbook also has that the steel has a fracturing stress of 5 times 10 to the 8th newtons per meter squared. So I use this to find that the force required to stretch and break a steel wire would be 1,600 newtons. So in our previous scenario where we were applying 980 newtons onto the object, we're kind of almost like halfway to that location, a little bit more than that. So we're actually close to fracturing that wire. All right, now one thing to note is you'll notice that in some of my slides, I have these little symbols at the top. These symbols, which I call viruses, are meant to say that this is extra information. This is information that I am not going to grade you on. I'm not going to test you on. You're not expected to know it for tests. And if I ask you a question on a homework, it's mainly a one-off question. And I most likely won't even focus on it. So for the most part, you don't need to worry about this. However, the reason I put this here is because I want, again, because a lot of people are moving on to engineering or higher level physics, I want them to at least be aware of this topic existence. I'm barely even going to go over this stuff a lot of times. So here is kind of a short little example about the stress of materials and how, like, depending on how you connect things will change how much stress an object will experience. Now you can go into a little bit more detail with this at your own leisure. I'm just going to briefly go through it. So in this side here, we have a single beam and there's a pin right at this location holding up this and that. So here, this pin is only really supporting the weight of this walkway. However, if we split it up so now there's two beams, so there's a beam up here supporting this and a beam over here supporting this. Well, while the net force at this location will still be the same of being an mg going up, it turns out that by splitting into two pins, we actually end up doubling the force that this pin will end up feeling. This pin will feel the weight of this being pulling it down, and this is going to feel the weight of this and this having to pull it up. So this ends up doing double duty at that location. So this type of scenario is going to end up resulting in a problem. All right, so here is a truss. So this is a type of bridge. I'm barely even going to talk about these. I'm actually going to probably skim a lot of this stuff. But this is something that those engineers kids are probably going to deal with later on. Basically, a lot of these rods are considered massless, and they're connected in a way so that their compressions and tensions result in allowing for a lot of force to kind of being able to pass through this, allowing it to kind of almost distribute a lot of that weight across everything. Now, it's important that these forces are end up being equal and opposite so that we don't have a torque on the object. Now, because there's actual weight on these beams, typically you end up having a scenario where you have to be aware that the forces actually can't be exactly equal and opposite. They have to be, one has to be slightly bigger than the other. Another thing that we could talk about, or something that we can deal with in this topic, is arches and domes. Of course, we're not covering this, but here are two examples where we kind of include how this affects torque. So if we look at the force on the hinge, we can actually use our torque equation. We're going to ignore the whole angle effect on it, and we end up getting that the force at the over here at one of the supports horizontally is about 3 times 10 to the 4th newtons, while here we end up having a scenario with this much higher arch being a little bit less. So when you have this semicircle, it ends up having requiring much more force going horizontally than it does vertically, or more horizontally than in a case like this, which only requires a little bit of force horizontal, since most of the weight is actually going up and down versus this, where it's kind of distributed all around. All right, so that's pretty much the end. We talked about a lot of stuff. Some of the stuff that we talked about the conditions for equilibrium, some of the forces, and some of the torques. We talked about how we can set up rotations in order to figure out, get rid of a lot of the unknowns and find what we're looking for. And then we also talked a little bit about stable equilibrium, and we also talked about, Hooke's law and stress and strain and fracture and all that stuff. All right, so this is the homework question. So the homework question is going to be from chapter 12. It should be due Friday. Now, if the due date changes, I will make an announcement. So keep an eye out for announcements because the date may change. But these are based off the problems in the textbook. Now, there are the 3 chapters that we're dealing with are the equilibrium questions, elasticity, and the fracture. Now, one thing I want to point out real quick, I had mentioned before that homework questions like these can be used to know where to focus for the test. This is what I mean. If you look here, 7 of the 10 questions that I've asked are going to be from the equilibrium section. So that means that when I give you a question on the test that you end up taking, the question from chapter 12 is going to be mainly focusing on the equilibrium section. Now, it doesn't mean that these two won't have a question. It just means that in the multi-parts, because there's going to be a part A, a part B, a part C, one of the parts might be about elasticity and fracture, but most of the other parts are going to be focusing on equilibrium. So the question is going to be about, I think it's going to be worth 10 points. I would say, almost the way these numbers are, 70 to 80% of the points are going to be on equilibrium stuff, some of the forces, some of the torques, and then 20 to 30% of the points are going to be using things like Hooke's law, Young's modulus, finding the change in the length, or fracture. All right. Now, if you want, there's going to be a 3rd video that you can watch where I go through some of the practice extra problems at the end of the slides. If you want, you can work on them yourself and then come find the video later on. All right, see you later until the next day.